Nicole has over 50 years of experience in information security and digital forensics from both commercial and government sectors. She is a computer crime investigator for the Air Force Office of Special Investigations, and she's a CISSP and holds three professional certifications in digital forensics. She's published several articles related to information security and digital forensics, IEEE transactions of information forensics security, decision support systems, digital investigation, and other journals. Her research interests include digital forensics, computational forensics, information security, and data analytics. Okay, Nicole, go.
Thank you, Max. Can everybody hear me? Is that on? Okay, great. Thank you for having me here this afternoon. Thank you, HoneyNet folks, for coming to San Antonio. I hope you found a good howdy and a good welcome here from us. Thank y'all for being here. Like I said, I'm Nicole, and the topic of my talk is advancements in computational digital forensics. I kind of threw the little carrot in there for digital because computational forensics has been around for quite a while, and I think, though, that the aspect of computational digital forensics is a little bit more behind, and hopefully I'll make that case for you today. Some of the projects I'm going to talk to you about today have been grant funded, and so I've got to put the disclaimer up there that the opinions I share are those of me and not the funding institutions. Last night I took about 10 slides out and a few projects out, so that insert above agencies here made a lot more sense last night, but took a few of those out. So anyway, I want to try and convince you first why we have an information overload problem. I probably don't need to spend a lot of time on that in this particular audience because all y'all, well, if you didn't feel like you had an information overload problem, you just heard one. Because that, not the speech itself, but the amount of data that he has is just amazing. Talk about computational forensics as a solution to that problem, and then I'm just going to show you a few examples, some that we've created here at UTSA, some that we haven't created here at UTSA, in 3 different areas of digital forensics. So the current situation, okay, you got the proverbial looking for the needle in a haystack. And I've heard a lot of people say that, well, we're really not looking for a needle in a haystack, we're looking for a needle in a stack of needles. I philosophically a little bit disagree with that because I still think at the end of the day, the stuff you're looking for is inherently to some extent different, a hidden process, though it's a process, but it's still delinked of some sort or whatever it happens to be, or the email that you're looking for where somebody says they were trying to kill somebody is inherently different than the email you get about being late for work. Or maybe that's why they want to kill you, I'm not sure. Anyway, so I still think you're looking for a needle in a haystack, but I think the difference is you're looking for a needle not in a haystack, you're looking for a needle in a hayfield. So, of course, the result of that is data overload, information overload. Now, when I first got into this business in the mid-90s, we had one person, one computer, and then how did you scale with that? Well, you threw more people and more computers at the problem, right? Then in the mid-2000s, oh, yay, we have distributed processing, distributed computing, and so we can, password crack and index on multiple servers, and I think that there's been a lot of advances in that even though now today, but I think even if you look at the distributed computing and Hadoop and HDFS and Elasticsearch and all those, still at the end of the day, you're still using more compute power, but have you really transformed the information overload problem? In digital forensics, I think it's even more behind. What we've done since then is, well, let's just have better case management, better data flow, better interconnectivity, and all that good kind of stuff, but I still think that we're still inherently in an information overload kind of situation here. And so my question is when are our tools going to get smarter? When are we going to stop working harder, throwing more people, throwing more compute at the problem, and actually have tools? And in fact, wherever Rafi is, the talk you're going to have next, really what I'd like to just do is shadow him for about a year because that's kind of the direction we need to head, where we have better visualization and smarter tools. What is computational forensics? I shouldn't say computational forensics is an emerging research domain. I think computational digital forensics is an emergent research domain. It concerns the investigation of forensic problems using computational methods, using computer-based mathematical models and quantitative analytics. Inherently, it's kind of the intersection between forensics, data analytics, and high-performance computing, and it's that sweet spot in the middle. There was a bit of a clarion call about 8 years ago for doing more computational digital forensics. This is in the lecture notes of computer science. And basically they said, hey, we need to work on these things in this field. We need to have a way to reveal digital evidence traces better, analyze that evidence objectively and make it more reproducible, search large volumes of data efficiently. This is not a surprise to you guys. Visualize that stuff better, et cetera, et cetera, et cetera. And that was 8 years ago, and I'm just not convinced that we've had a lot to show for it since then. I think if you look at computational forensics in the larger sense, you've got the traditional stuff, right? You've got, this is my favorite topic, you've got blood and bullets and toxicology and those kinds of things. And we've applied computational forensic methods to that space. We've got increased DNA typing. We've got increased ability to do toxicology studies and those types of things. But inherently, if you think about it, the underlying stuff that you're doing that computational forensics on hasn't changed very much, right? We're still the same humans. Our bullets have had, punctuated equilibrium moments of change, hollow point, ooh, that was a big change, right? But I mean, the underlying stuff that you're doing forensics on hasn't changed very much. But if you look at it from the digital forensics perspective, and you look at that list on the right there, these technologies, these things, that stuff that you're doing forensics on changes. It changes fast, and it changes a lot, right? What is cloud forensics? What is mobile forensics? Mobile forensics today doesn't look like mobile forensics tomorrow. Just the space, the data structures, the encryption, the encoding, everything changes so quickly. And so we have a change problem that you don't have in the traditional computational forensics. Furthermore, you have a data problem that, you got the proverbial exponential growth of data. But I would make an argument that compared to regular forensics, traditional forensics versus digital forensics, you've got more and more and more data. Not only is the data changing, you've got more and more data to deal with where we need computational forensics to help us out, otherwise we're going to be underwater. So I just want to talk to you about a few different cases, not cases, specific cases, like application spaces for computational digital forensics. We're going to talk about document search and triage, a couple of solutions there, data type classification, and malware, which has probably been discussed enough today. But this tool was a tool that we developed here at UTSA called Sifter. And how many of you guys have done digital forensics with like a traditional digital forensics tool, like SIFT or FTK or you name it, whatever? Okay, so how many of you guys have Googled? Okay, just making sure you're awake. So if you haven't noticed, last time you Googled, or go do it right now if you're bored, go Google something. Go Google restaurant, Mexican restaurant in San Antonio. You'll get, how many search hits do you think you'll get back? Oh, about 6 million or so. 6 million hits returned in 0.3 seconds. Awesome. Why do you use Google? Because it ranks stuff, right? It's useful. When is the last time anybody has gone past the 10th page, 17th page when you're searching, right? So it can bring back millions of hits, and that's fine for you because the stuff that you're looking for is pretty well ranked at the top, and you get what you're looking for pretty quickly. That's a useful thing. So for those of you guys who raised your hands and said you've done digital forensics with traditional tools, how many of you guys enjoy or ever do, probably never anymore, text string searching? Anybody? Why? Why not? Because it's horrible, right? There's no ranking algorithms. The best advancements in our tools these days have been things like, let's put all the search hits results for this thing in a kind of a type class bucket. These are all your document results. These are all your graphics results. These are all your whatever results. But when you think about just even a single disk, and you talk about the unallocated space and the allocated space, you've got so much noise. You've got a signal-to-noise ratio that it's 5% if you're lucky, which is really probably less than 1%. And so you've got so little signal to noise that, and if you don't have a ranking algorithm like we enjoy with Google, you're really set looking through millions and millions and millions and millions of search hits, and you're just hoping a relevant thing is at the beginning and not the end, right? So what Sifter was built to do was basically said, let's take some intelligent computational approaches to string search hit analysis. Let's try to rank it. Let's try to put it in a perspective that's more useful to the analyst. Let's try to get the analyst to the useful stuff more quickly. What you see at the bottom there is not just a throwback to the Tandy TRS-80 pixelated. This is actually a self-organizing neural network that takes the string search hits back and then puts them. It uses a bag of words approach to thematically cluster any kind of object that came back with that search hit, whether that's a sector in unallocated space or a document or whatnot. There is hue, color, saturation, and luminance that all mean something in this particular space. And so the things that are colored similarly mean that those clusters are thematically related. And what you see over there, the 0 and the 1 and the 3 and the numbers and the text underneath there, those don't really exist in the tool. You see at the top level, if you can see that, there's a text line. And as you scroll across this were an interactive example, as you scroll across, do I have a mouse that works here? A pointer? No. As you scroll across a cell, those are some of the strings that occur in that. So you can very quickly see, hey, this is the text region, this is the web region, this is the graphics region, this is the whatever region. And so you can narrow in depending on the type of artifact you're looking for and find the objects of the type that you're looking for. And then the color region brings like a self-organizing network, brings the regional similarity together. Then the saturation of the cell shows the density. It's a cluster base, so the density of the objects that are in that cluster, the more saturated the color would be in that. And so if you want to find a cell that has a lot of very thematically related things that are very densely clustered, you would go to a very saturated colored cell. And then luminance. Actually, the darker the less luminance means the larger the cell is, the more objects that are in that cell. And so if you really wanted to very quickly figure out where the evidence is that you're looking for, you could, I guess a colorblind forensic analyst in this particular case would be in trouble. But for the folks that are not colorblind, you could use a very graphical, color-based mechanism to find the things you're looking for. And then if you were to implement, which we haven't done in this particular iteration, some sort of relevancy feedback, the tool could actually navigate you to the things you're looking for more quickly. And then you have the traditional click on a cell, click on a hit within that cell, and you get what's shown up in the text there, which is the text of that thing. It accepts Boolean queries and all the normal things. What you see on the top in the table, you'll see the second column says score. That is an attempt to be the Google for digital forensics. The Google ranking algorithm for Google is to digital forensics. We would love to have our search hits ranked. And so what that score is based on, if you think about, well, why don't you just apply the Google ranking algorithm to digital forensics string search hits? Well, a lot of the features don't apply, right? We don't have a traditional web structure. We don't have linkages and stuff like that. And so what we did was we did a machine learning-based approach to determine relevancy and not relevancy, and then trained the classifier. And basically, based on these features in the things that came back, we can basically then basically take a binary classifier, take the weights from those features, and create a linear discriminant function to create a rank of those hits. And so you could use Sifter just as a ranked output list, or you could use it for the self-organizing neural network, or you could actually use them together. So it's just an example of something that you could do, and you could transform digital forensics by having a more intelligent approach to your tools. One of the features we found, and this tells you about it, but I think I've already told you most of that. So in the interest of time, one of the things that we needed to do when we created that ranking algorithm is, if you think about it, the type of hit that you're looking for, the type of data that hit occurred in is quite relevant to your case. If you're doing an intrusion case and you find a string that exists in a binary, well, that's more relevant to you than something that existed in email. Conversely, if you're doing a traditional murder case and you find a string that existed in what used to be an email, or what used to be a Word doc, or what used to be whatever, that would be more relevant to you than that same string found in a block that used to be part of an executable. And so data type classification becomes important. And it's important particularly in unallocated space when you no longer have a file signature, you no longer have the file system metadata, you no longer have anything that you used to have to tell you what kind of file this thing used to be. So we basically needed a data type classifier. Some cases for that, like I said, what we needed it for was for our ranking algorithm. You could also use data type classification from a triage or disk profiling perspective. We actually had one of the projects I took out was a kind of a disk profiling based approach for insider threat, in which case you want to type classify unallocated space and find out what is on that drive. May help with fragment identification and recovery, intrusion detection, just identifying payloads that are inconsistent with a reported file type, could not necessarily be definitive to you, but could possibly help with your triage, could help you maybe direct your DPI, deep packet inspection resources. So there's a few different applications. Those of you guys who are in the data classification space knows there's two fundamental camps on how you do that. You can do it naive statistical classification, just look at characteristics of the data and statistically classify it based on that, or you could take a more semantic-based approach and say, well, I know that there's a lot of FFD9s and FF00s and JPEGs. I know I can look for the end stream, begin stream tags and PDFs and so on and so forth. And so there's kind of two fundamental camps. I personally think the more intelligent approach is a hybrid of that, but that's not the point here. What we were trying to do was create a naive statistical classifier. For those of you guys who aren't convinced why that's important, this is just a slide that shows really simple byte frequency distribution of 6 different file types. I actually, okay, I can see if I'm this close. Doc, executable, HTML, GIF, JPEG, and PDF. And what you've got there on the x-axis is all 256 byte values, unigram, just single bytes. And so you see the frequency distribution, histogram of the frequency distribution of those bytes across different file types is actually quite different. And this is not new. This is not new stuff. This is just showing you guys why this works. And so what we were trying to do is build an accurate classifier. We built a classifier. Max just told me I can slow down. I don't slow down very well, but okay, I'll try. We wanted to build a classifier with about 50 different data types. We wanted to, of course, achieve high accuracy, because what good is a classifier if it doesn't classify accurately? That's another good philosophical discussion, because if you get into some communities that have used some of the stuff we've done, they say, well, if it's not 99% accurate, what use is it? There's a lot of uses for stuff that is not necessarily 99% accurate. But anyway, large multi-class model. We wanted to include different challenging data types that had not been studied before. We wanted to empirically reduce the number of dimensions that we needed to do the classification. So in other words, do we have to classify, do we need all 256 byte values to classify something? Because the less features we have, the quicker we can do our computation, and the smaller our vectors are, and the computation is less significant. Do we need all of the byte values? Can we classify file types not using the entire byte stream? And so if so, determine what those are. And then we also wanted to determine if we could do hierarchical classification. In any kind of classification model, just statistically, if you're trying to classify something in 2 different classes, you have a 50% chance of getting it right? If you want to classify it in 100 different classes, your statistical probability of random chance proper classification goes down quite a bit. And so it's a fundamental truth. If I can reduce the number of classes, I can improve my classification accuracy. This was actually argued by some folks at West Point several years back, and says, hey, why don't we do hierarchical classification? Why don't we classify stuff into a class, and then from that class, classify it into a type within that class? And so that's what we set off to do. This is a slide that shows, we're not alone in this area of research. This is a general slide. You've got prediction accuracy on the y-axis. You've got number of classes on the x-axis. And basically it shows a negatively sloped line to say, well, your prediction accuracy goes down by the number of classes you try to classify data in. That's kind of obvious. Great. We are the outlier, though, on the right, and that shows we're at about 76% prediction accuracy. That's actually, it was 3 years ago. I guess I just need to update my graph, but I'm too lazy to do so. We're up in the 80s now. But nonetheless, we're an outlier, and that's a good outlier to be. The fewer classes you have, the higher prediction accuracy you can get, and the more classes you have, the more prediction accuracy goes down. We had about we've gone up to 52 classes since then. That slide shows 38. But one of the things I want to point out there is in the past research, you've got these green diamonds, the yellow triangles, and the red circles. So a lot of the researchers achieved these awesome classification accuracies because they used, what do you think? When they trained their classifiers on how to identify file types by class, do you think they used the whole file? Yes, and they used the header block. Why is that bad? It's kind of cheating, right? It's got the file signature in it. And if you're doing an n-gram-based byte, classification type approach, and you include the file signature, guess what? You're going to be pretty good. It's called file. Or TRID, whatever you want to do. The yellow triangles are the ones that not every sample had had the file header in it, but some of them did. And the green ones are the ones that completely took out, in my opinion, did the most purist research and took out that header block, so they weren't kind of stacking the deck by including the header sector of the files. This next slide shows, that kind of answers the question, do we need all the bytes? This is just one example. This is an exe file. On the y-axis, you see the byte distribution, so 0 to FF. And then on the x-axis, you see the discrimination value, the feature weight from the classifier. And you see, and then there's actually 4 different experiments run, that's the different colors. But you basically see that most of them are kind of, they're about at 0, a little less than 0, so most of them don't hold a lot of discriminatory value. The ones that are the outliers, the one that are the highly negative or the highly positive, I don't care whether it's highly discriminatory to say it's not an exe, or if it's highly discriminatory to say it is an exe, whatever. I just want to know what are the byte values that help me classify an exe. And you can see that there's very few outliers, and that was actually a very cool thing. And then that held across most file types. This is an example of an MP4. I could have picked any of them. But what we found was that it really is about 15 to 20% in any given file type. Only about 15 to 20% of the byte values. And we actually did unigrams, 1 byte, and bigrams. We actually went up to trigrams. But there's only about 15 to 20% of the n-grams are needed to actually classify a particular file in a file type. So those of you guys who do classification means your vector just got a lot smaller, especially if you're talking about bigrams and trigrams. So that was a really cool finding. Now if you're sitting there going, well, okay, that's great, Nicole, but if I have 20% of the n-grams for executables and a different 20% for MP whatevers and a different 20% for eventually am I back to needing the entire byte space? I didn't put a slide in there, but we figured that out too, and figured out, no, there's actually a smaller percentage of the shared n-grams across these 52 file types that were actually effective in classifying. So we can, it turns out, and this is really important from the standpoint if you ever want to use this stuff from like a intrusion detection, looking at packets as they come across the line and doing it very quickly, you want to get those feature vectors as small as you can, and this research showed that you can do that. What the graph there just shows that your performance accuracy drops quite significantly after about, in this case, 22% of the n-grams. With regard to the hierarchical classification modeling, I already mentioned that. We did do several experiments in that. We tried several different hierarchical classifications. I don't want you to get real wrapped around the axle either about this particular hierarchical model nor the descriptive titles of those hierarchicals, because to some extent this is the classic academic research of proving the painfully obvious that high entropy file types will cluster together and text-based file types will cluster together and so on and so forth. But the biggest issue, I would say two things. One, if you're going to do hierarchical classifier, you make it case specific to what you're trying to classify. And so that's why I don't think this particular table is particularly probative for everybody's use. You want to build a application-specific hierarchical classifier for what you're trying to classify. But the point is that you can improve your classification accuracy. You got pretty good classification accuracy at the class level, and then at the type level, you still have pretty good classification accuracy. And of course, your type level classification accuracies are much lower in your high entropy types and are quite high in your non-high entropy types. So with that, those are just some examples. On malware analysis, these are not examples of UTSA research, but are examples of some things that I think are pretty fun. Malware classification. This is just some more creative stuff from malware classification. So if you take, again, I guess I love n-grams. So if you take n-grams and you take all 256 byte values and you basically then create shades of gray for all those, it's a lot more than your 50 shades of gray. Okay, anyway, and you do a 256 grayscale image of your binary, and you create that kind of big vector, you get an image, a picture of your binary that could look like this. And you actually see it does a pretty good job at, because of the differences in the binary and the data in the binary, you get pretty good distinct section regions. Okay, so who cares? But what's interesting about that is is it looks tremendously different across different binaries, right? These are all different malware binaries, and look just graphically at how different these things look. Okay, great, Nicole, so how are you going to type anything with that? Pretty pictures. I think this picture shows it a lot more. So what you see on the top row is these are three different variants of the same binary, or three different variants of binaries in the same malware family. And then the bottom is three different variants of a different malware family. And as you computer science folks know, there's a lot of very advanced approaches for doing graphics similarity measurements and finding the similarity of graphic files. And so if you wanted to very quickly triage and say, hey, I've got a new observable, I've got a new piece of malware, this is one of many ways you might be able to very quickly type classify in a particular malware family and then go do your reverse engineering from there, or if you just need to quickly assess its risk. So I just think that's pretty cool. Classification via instruction frequencies, and so you've got your binary and you disassemble and you've got all these different instructions. The top graph shows the instruction frequency, so on the x-axis is just an index of the instructions in that binary. On the y-axis is the instruction frequency, so for every given instruction, what is the percentage, the rate of that instruction for that particular binary. And what you see, the top one, the blue X, if you can discern that, those are the ones that are kind of floating up higher. That's a piece of malware in family A. And then the bottom three, the red square, green triangle, and purple dot, those are variants of a different malware family. And you'll see, if you look, that the red square and the green triangle and the purple circle are all hanging out together. And that's kind of would make sense, right? It's the variants of the same family have similar instruction frequency profiles compared to the instruction frequency profile on a piece of malware from a different family. You see a lot of variance in there, right? The bottom one is the instruction frequency in normal programs. And so what you observe there is that the instruction frequencies in benign programs tends to be a lot lower. In other words, there's a lot more heterogeneity in instructions, in use of instructions in benign software than there is in malware software. We use a lot more different instructions in our benign software than we tend to use in our malware samples. This next graph is also interesting because this is a box plot of kind of, it's another take on what you just saw on the previous screen. The blue box plot, so that's the benign software. And so what you see is across two different pieces of benign software, the instruction frequency, the variance in that instruction frequency across different normal pieces of software is really high. So in a piece of software A versus piece of software B, the same instructions will be used in a very different profile of frequency. The middle one, the red one, is instruction. You see inconsistent variants of instruction frequency across malware binaries in different families. And so if you compare the instruction sets in malware family A versus malware family B, you're going to see a much greater range. There's going to be a lot more variation across those frequencies. And then the green ones there is now variance within the same malware family. And again, it shows that you have a very low variance across samples in the same, across variants in the same malware family. So I think it's interesting. Is this going to help you phylogenetically type malware? No, not necessarily, but it gives you insight. It gives you insight into, hey, actually instruction set frequencies and what instructions are used in malware can actually help you with your type classification. And the next slide, I think, is probably one of my favorites. This is just my pitch. I keep trying to get in my offices at UTSA. They've got millions of dollars of art budgets, and they keep telling me what I think is art is not art, and they keep giving me art that's I guess art. But this is art. Okay, so what this is, so on the left there you see these are these are control flow graphs of malware samples. And so they look like spaghetti plots. And, you know, if you've seen one spaghetti plot, you've seen them all, and they all look about the same, right? But they're not. They actually are, if you look at the traces from these executables, they are actually quite different. And so what you see on the right, this is what I've told UTSA I want them to buy me for our labs and our offices. This is a guy from MIT. He's a multimedia guy and a computer scientist guy, and basically he's taken control flow and trace visualization diagrams and basically did an artistic rendition. And so what you see there is two different viruses, old ones, but you got MyDoom and Configure. And so aside, I guess, if I do this in my office, if people walk by, they'll think that I'm an oceanography department of some sort, because I think it probably looks like coral reef or whatever. But I mean, it just visually, right? To think that, I think they're actually quite pretty, don't you? Anybody else? Geek art is actually pretty. But it really highlights how different those trace visualization and control flow graphs are. And then from a realistic perspective, not that you'd use the art version, but, you know, the control of another area of malware classification is doing the control flow graphs of the malware itself, and then doing through graph theory and graph visualization, and then do similarity metrics of the different graphs. And so I think those are just some really interesting examples of how to use computational approaches, advanced machine learning, and artificial intelligence to make our tools smarter in the digital forensics space. So my thoughts and my soapbox. This is, I usually use this slide if I'm actually talking about to law enforcement people, because I've talked to some of the digital forensics folks and vendors and asked why they don't do this kind of stuff. And the answer that I get back, it just frustrates me quite a bit, because they said because the baseline capability keeps 80 to 90 or more % of the forensic investigators happy, and they don't even know what they don't have, and they don't know probably even how to use it if we put this advanced stuff in the tools, which just drives me batty. But so I kind of try to tell folks that they need to demand these, that they can have smarter tools. A lot of folks don't even understand that. I mean, what are the big advances in digital forensics tools in the last decade or so? Okay, so we've added fuzzy hashing. Great, thanks. So we've added some skin tone detection in our graphics utilization, so we can kind of put the investigators on the images of people and stuff, and that's helpful. But that's really not what we can do in the computer science field for digital forensics. And so I just try to tell people that, they're not going to get these smarter tools unless they demand it. So this is a bit of my soapbox. And I try to tell them, too, if they want to pick up a new intellectual hobby, pick up machine learning, AI, and data analytics, and then you'll really know what your forensics tools can do for you. So with that, I just kind of want to talk about the digital forensics space for a few minutes, try to convince you guys that I think that the information overload problem for us in our field is pretty large. I really, 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 really think that in our field we've used... Do you guys remember the Mac and PC commercials? Right? Those are the best. And remember what the most exciting application was in PCs? Anybody? Calc. I think it was Calc, right? And I would kind of contend that we're using, even if we've got these great Elasticsearch and all these different platforms, we're still using our computers as pretty dumb machines as it pertains to digital forensics. We're really using these machines, and I think the analog of Calc, to do our forensic cases. And if hopefully I've just convinced you of that a little bit, and giving you a few examples of how we can fundamentally change how we do digital forensics in our space. So with that, I think I have a bit of extra time for some questions, if anybody has any. I did good, Max. I even got you done early. Sure.
Really back to the art stuff.
Yeah.
Have you done more than that? Where we say, oh, look, I see some characteristics of this way, I see those things like your comment about, wow, you really went right to really kind of interesting. And I thought, where could we take that analogy?
take the visual analogy?
Yeah, take that visual analogy. Oh, here's a virus like in the bloodstream, but it's really a computer virus, and here's its shape. And, because viruses often they have little contact points and all sorts of things in biology. So how do you relate this to biology?
Well, there's some really good examples. I don't know if this gets to your visualization aspect, but a lot of people don't know about these examples. So a lot of you guys know about the Digital Ants program, right? Yes, no? How many of you guys have heard of Digital Ants? Digital Ants, PNNL, basically saying, well, and I've got a 7-year-old son, 8-year-old son, and he loves to throw a rock at an anthill because it's just cool to see the ants mobilize and what do they do. And the ants have these communication protocols that are autonomous, and they know what to do, and they can communicate with one another. And I guess I should stand over here because I'm echoing over there. And so basically what PNNL did is discuss, well, how can we take the digital analogy of ants, and they created the Digital Ants program. So you can put these sentinels on networks and have sensors, and something's going wrong, and so mobilize different ants to do reactionary things. And so that's kind of a bio-inspired cyber defense. The analog to that on the other side is a little less clear for people. How many of you guys have heard of the World Health Organization's recent announcement of using the Conficker worm, the propagation model for the Conficker worm, as a model that helped them understand, and forgive me, I'm not a biologist, so if I say this wrong, you can criticize me, but for slowing down the advancement from HIV to AIDS. They found that the propagation of HIV to AIDS could be modeled very similarly off the propagation model of the Conficker virus. And so that doesn't really answer your visual part of your question, but it does answer, I think, part of I think that there's a lot of analogies between the biological pathogen and the digital pathogen, a lot of similarities. And I think that if we could get ourselves out of our little myopic worlds that we're in, we could have a lot more inspired solutions to our answers, or to our questions that we have in that space.
Cool. Any other questions for Nicole? Yep.
Say that again.
I have 5 fragmentations when the file is distributed across this image. So my problem was always that I couldn't figure out which part of...
How to put Humpty Dumpty back together again?
Yes.
No, we haven't actually taken our stuff and applied it to file fragmentation, is the short answer to your question.
Okay. The second problem was container file types, images inside.
For images inside the file types?
Container file types. So if you have an image, a document, or a PDF,
Yes.
when they contain images or macros or a HTML file with JavaScript inside, are you able to identify those container types?
Yes. The short answer to your question is yes. So we did our experiments both on the entire file type, which could be a mix of files and file types in it. So at the primitive object level and at the container object level, and we did experiments on both. So.
Okay, thanks.
Any other questions? Okay, wow, thank you, Nicole. That was really fabulous.